Hi, I'm Ben-Yaakov. This presentation is entitled MOSFET Junction Temperature in Power Inverters as related to low phase frequency, thermal conduction, and thermal capacity. I'd like to thank Evgeny for reviewing this presentation and supporting the preparation of the video. So what's the issue that we are going to discuss here? The question is how to estimate the junction temperature of MOSFETs in a power inverter. I'm showing here a half bridge, could be part of a three-phase inverter. This is like a permanent magnet motor, for example. It's the back EMF. This is the phase impedance, inductance, and resistance. And then we have the two switches, MOSFET, which are toggling here, producing in some application a sinusoidal waveform. This switch now, the upper switch, will see current like this because it's turned on and off. The current of the inductor is passing through this transistor. So you see here periods of current and then no current, and this will be the shape of the current within this transistor. So the question is, how can we estimate the maximum junction temperature of this and this transistor? Now, the relevant parameters are, of course, the current amplitude of the phase, the frequency of the waveform, thermal conduction of the MOSFET, thermal conduction of the heatsink, we are going to talk about it, thermal capacity of the MOSFET, and also thermal capacity of the heatsink. These are the subject matter of this presentation. So I'm going to work with this model, that is, rather than looking at the ripple here, I'll assume a sinusoidal waveform for the phase current so that I don't have to worry about the additional RMS due to the ripple. So what are the losses? First of all, we have conduction losses, which are due to the fact that the transistor do have a resistance while in the on state. I'm talking about MOSFETs. So when the current is passing through this RDS on, obviously we have conduction losses, which will increase the temperature of the device. So this is one of the losses that actually in many applications is a major loss. But then we have the switching losses, which are due to the fact that when switching a transistor, and I'm showing, say, the voltage and current of, say, this transistor. So when the transistor is turned on, current is rising. We have a period of an overlap between the voltage and current on the transistor, and consequently we have some energy loss, current times voltage, and times the frequency, this will be the power loss of the device. So these are the two losses. The conduction loss is proportional to the square of the RMS current. I square times R is the power loss, while the switching losses are actually for a given bus voltage, high voltage, then the losses will be proportional to the current, current at a given point. I'm calling it DC, that's not DC, I'm just saying that's not the RMS, but the actual current at any given point. And over the cycle, it will be approximately proportional to the DC value. Now, what about the conduction losses? We look at the half bridge, we have two resistors which are being connected one at a time to the phase current. I'm assuming that the RMS here is about constant, and the actual current, of course, is, say, sinusoidal. Now, as we understand, the current is seeing RDS on anytime. That is, when this switch is on, it says RDS on here, and when this switch is on, it says RDS on here. So we can say that the power per transistor will be RDS on IRMS square over 2. This would be a very simplistic way to estimate the power loss per transistor, and as we'll see, this is really an approximation, and in many cases you have to refine it. What about the switching losses? It is proportional to the DC, as I've said, times the high voltage, bus voltage, times the frequency, and of course a constant which will take into account the rise time and fall time of the transitions. So the temperature now of the junction will be a function of the power loss within the transistor, say it's the upper transistor, and we have a very simple model that emulates the thermal effect or thermal conduction here. The power is like a current source, and then we have the thermal resistances, which are like resistors, and temperature is emulated by a voltage. So the junction temperature will be the current or the power flowing throughout these thermal resistances plus this temperature, the ambient temperature. This will be the junction. But hold on, what happens at low phase current frequency? Suppose the frequency is low, say 1 hertz, 0.1 hertz, or if you wish, the period is once a day. Well, obviously, you are spending a lot of time at the maximum here, and therefore you cannot assume that the RMS is really representing the situation. So the junction temperature within this cycle, if it is of low frequency, will actually go up and down, up and down. It's not going to be a fixed temperature. And the question is, of course, how high will it go and how does it depend on the thermal components of the system? So this is the issue that I'm going to discuss here. To see, first of all, what is the actual current passing through the transistor and what is the power loss during a cycle of the phase current, I've set up this simple PC, actually from a demo that I've borrowed, and I'm measuring the current of the transistor. I'm squaring it to get I square, and then I am sort of integrating it on this 1 farad capacitor to get a measure of the energy lost. Okay, so that's very simple. This is just a 3-phase modulator, and here we have a 3-phase inverter. So here is what I get. The red here is the phase current. The blue here is the switch current, and this is the energy loss. Now, in order to understand what's going on here, you see the current is here. So I've just marked it. So here is the current, here is the current, there is a void here, no current, zero current. But notice, very important, that this is not symmetrical. During the second half cycle, here is the current, this is no current, so the total power here lost is lower than the total power lost here. Now, obviously, this is for a outgoing current, okay? This is for a current like this. Now, if the current will be ingoing, it'll be reversed. So over a long period of time, the average is the same. So one can say that the dissipation of the transistor at each half cycle is the same. But this is for high frequency. At low frequency, this is incorrect. So these are the issues that need to be taken into account, and you can see it here. This is the energy lost during this half cycle, and this is the energy lost during this half cycle. So they are definitely much different, and of course it is a function of the modulation index, depending what is the average magnitude of the voltage that you are generating. Okay, so it is not a general plot here, but it is for this particular point that I've simulated. So let's go back one step and see what are the frequencies that you'd expect in a typical application. And I'm considering here an inverter which is feeding, say, a permanent magnet motor, a brushless permanent magnet motor. So here we have the inverter. This is the 3-phase, and the frequency of the phase current is related to the RPM by this equation, RPM of the motor itself. And this will be RPM over 60 because this is per minute. And then times the number of poles divided by 2. Because the higher the number of poles, the higher the frequency you have to feed in order to complete, or you have more cycles of electrical cycle per one mechanical cycle. Okay, so this is the electrical frequency of this waveform here, and this is the RPM of the motor. So let's just take an example just to get a feeling where we are at. So let's take an example. Suppose we have a motor which is running a vehicle, could be a personal mobility or electrical car, and let's assume that at 5,000 RPM, the speed of the vehicle is 100 kilometers per hour. Okay, this would mean that 50 RPM is 1 kilometer per hour, and if we assume a number of poles 8, then we find out that the frequency for 1 kilometer per hour is 3.3 hertz, fairly low. And 1 hertz corresponds to 0.3 kilometer per hour. So if the speed is below, say, 0.3, in this case, 0.3 kilometer per hour, we are going to have a sub-hertz frequency, low frequency. And this will be like when parking, for example, or starting, you may have this low frequency. So therefore, in this case, we are to expect that the junction temperature is not going to be constant. It's going to change depending on the instantaneous power that we are going to have. So for that, you have to take into account the thermal capacity. That is the ability of the system to absorb heat during transient thermal phenomena. And what we understand in that is that if we have, say, a step in the power loss, temperature of the junction is not going to jump immediately. It's going to rise exponentially, first order approximation, and with the time constant, we depend on these elements. And obviously, in the case of a motor, which is driven by a sinusoidal current, the power is pulsating, and therefore you would expect a change in the junction temperature, and the lower the frequency, the larger will be the ripple of the junction temperature. So let's talk a little bit about thermal time constant and the thermal mass. Now, if we have a mass of some material, then we can define the heat capacity as joule per degrees Kelvin rise. That is how much joule you need to raise the temperature by 1 Kelvin, 1 centigrade. And we obviously can talk about the specific heat capacity, which is the amount of energy you need to raise the temperature by 1 degree centigrade per gram. So if I am pumping into a mass some energy, thermal energy, this is a thermal loss due to, in the case of a transistor, the current and the resistance, then the expected temperature rise will be this energy over the mass, grams, and the specific heat capacity constant. So let's just take an example. A aluminum, which is commonly used for heat sinks, has a specific heat capacitor of 0.9 joule per centigrade per gram. So the thermal capacity is this constant, specific heat capacity, times the mass. So let's assume we have a piece of heat sink, which is 200 grams. Then we do have a thermal capacity of 180 joule per degree centigrade. So in order to simulate it, I'm using just a simplified equivalent circuit. In fact, it's a distributed system, but what I did here, I sort of divided the capacitance This is now an electrical capacitor, which represents the thermal capacitance. I'm dividing into two capacitances and two thermal resistances, okay? So this will sort of represent this heatsink, but we do have the transistor itself. Now, the transistor has also a heat capacity, so therefore, if you expose the transistor to a step power, that is, at a given point you start pumping in energy, it will rise. Well, depending on the model, depending on the structure, and as a first approximation, I'll assume it's a first order system. So the temperature will start rising, but if the pulse is short, okay, it's a short pulse, then obviously you'll get to a given point and that's it. And then, of course, the temperature will go down because the unit will be cooling down, okay? So you can therefore define an effective thermal conductance, or impedance as it is called, for a pulse, and it is related to the steady state thermal resistance times this expression for the time constant, okay? So if the on time of the pulse is very short, then you have an effective thermal resistance lower because the same power will raise the temperature to a lower value, okay? This is just an introduction to this plot. This is a plot that usually you'll find at power MOSFET transistors. And what it says is the following. This is the steady state thermal resistance. These curves are for pulse operation, either continuous pulses, and this is the duty cycle. So this is a pulse of 0.5 duty cycle, and this will be the on time of the pulse, okay? But this is a running pulses. The last curve here is for a single path, okay? So we can now use this last curve. You can see it's not a straight line. This is a log-log scale, and if this is the approximate equation, and if it is a log-log scale, this should be a straight line because it represents this equation. But it is not, because this transistor has a number of, you might say, compartments for thermal capacitance which exhibit themselves like a second order or third order. But let's assume this is a straight line, just for simplification. Now I can find out what is the time constant by looking at the point at which it will be one time constant apart from the steady state, like 0.6, okay? And here it is, the 0.6 of the 0.6, which happens to be the thermal resistance of this particular capacitor. So I'm looking when this drops by 0.6, that is 2.36, and I find that the time constant is 6 times 10 to the minus 3, that is 6 milliseconds, from which, and this is what I'm after, I can calculate that the thermal capacity is 10 to the minus 2 joule per degree centigrade. So by this, I have extracted a missing parameter for the model of the thermal model of the transistor, including the thermal capacity. So now I have the complete model for this particular example. So let's go back for a second to the heatsink. We have found that the thermal capacity of the heatsink is 180 joule per degree centigrade. And I'm going to assume that the total thermal resistance of this heatsink is 4 degree centigrade per watt. And as I've said before, I'm going to split it into two parts, and also the capacitance I'm going to split into. So this is the heatsink, and this is now the transistor. 0.6 is from the data sheet of this particular transistor, and 10 millijoule per degree centigrade is the thermal capacitor. And here is a run for a frequency of 100 hertz. Now, the steady state junction temperature should have been 55 degrees centigrade, and this will be for a peak power dissipation of 25 watt. Okay, this is just an example. And I'm assuming here ambient temperature 0, just that we don't have to add or subtract then temperature. So in the 100 hertz for this particular system, the junction temperature in this simulation comes to be very close to the steady state. There's a little bit of a ripple. Let's have a look at it here. This is the power dissipation. This is the average 55. And then here is the ripple in the actual system. I'm assuming here that the power loss in each half cycle of the phase current is the same. As I've said, this is incorrect, so you have to correct for it in any particular case. So this is a very simplified example. Now, what happens at 1 hertz? Well, we start to see the ripple growing up. The junction temperature now is getting up quite a bit. And if it is 0.1 hertz, I'm getting closer to the very upper limit, that is the temperature, assuming this power dissipation, okay? Because I'm spending quite a bit of time here, so I'm approaching it. And for 0.03 hertz, we are practically at the maximum. Now that's a big difference. It's almost, in the delta, it's about twice. So therefore, it is really something to consider if you expect some time at which the frequency of the phase current will be low, and you have to see how is the system coping with this situation. So we can summarize it as follows. If the RMS can be taken into account, then obviously the temperature will be calculated according to the RMS current. But if you are worried about very slow frequencies, then you have to take actually the peak, the period of the peak, and obviously the power of the peak, assuming a sinusoidal waveform for the power, it'll be a times square 2, so the effective current you have to take into account is the RMS of the phase times square root of 2 for the peak value. So if I assume for simplicity that the power in the two half cycles is the same, then as I've said before, the total power dissipation is I squared over RDS1, and then per transistor it will be divided by 2. And if the frequency is very low, then you shouldn't take the RMS, but rather the RMS times square root of 2, you end up with a power dissipation which is twice as large. And therefore the delta T will be twice as large as compared to the simple RMS case, which is correct for the high frequency. So what are the conclusions here? Well, thermal capacity plays an important role in the junction temperature. In practical cases, I've found that thermal frequencies of 0.1 to say to 1 hertz is sort of the borderline in practical high power systems. So in these cases, if you take a safety factor of say 1.1, you're on okay. But if the frequency is below, in the case of a vehicle, 0.5 kilometers per hour or much lower than that, then you have to worry about the temperature of the junction, and knowing that just taking the RMS or the phase current as a measure of the power dissipation is incorrect. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found this of interest, and perhaps it will be useful to you in the future. Thank you very much.